All right, so what can I do for you tonight?
Okay.
Welcome to review, final exam review.
Could you go over a relations problem for me? Which,
Sure. All right, binary relations. So you know what a binary relation is, right? It's any subset of a cross product of two sets. So here's an example. We can let A, for example, could be a set that contains, I don't know, like 2, 3, 4, and 5. And we can define a binary relation, curly R, on A. Now that means that R is actually a subset of A cross A, where the ordered pairs have both coordinates coming from A as follows. Uh, XY is in curly R if and only if, let's say, X is greater than Y. So we could find R, that could be part A, and then part B, we can draw the directed graph of R. Okay, so what we're doing is we're looking at A crossed with itself. And we're going to take ordered pairs, X comma Y, and put them in R if the first coordinate coming from this copy of A is larger than the second coordinate, just for example, as just an example problem, okay?
okay.
All right, so you help me. Let's build R. What would be a first, like, could we build any ordered pair where the first coordinate X would be 2?
Yes.
Oh, okay, tell me what ordered pair you think is going to satisfy this
Oh, okay. No, no, no.
relation. Okay, if it was less than, we could.
Yeah, yeah, yeah. Okay.
All
I
right.
see.
So two is not going to be greater than any of the elements in A, right? So so
Yeah.
so let's move on. How about 3? Could we build an order
Yes.
pair with 3?
With two.
All right, 3 comma 2. Good. Can 3 be the first coordinate for any other ordered pair?
Mm,
Is 3 bigger
no.
than anything other than
Nope.
2? Nope.
Nope.
Good.
Nope.
All right, how about 4? Can we use it for the first coordinate?
Yes.
With what?
Two.
All right. Can we build another order pair with 4, or is that it?
Yes. Four and three.
4, 3. Perfect. Anything else with 4 as the first coordinate?
Uh, that's it.
Okay. Moving on. What would be another order pair that we could put in here?
Five and two.
Okay. Anything else?
Five and three.
Uh-huh.
And five and four.
Exactly. And I think that's it.
Yep.
So now we're going to draw the directed graph. So the directed graph has a point for each of the elements in the underlying set. So we have a point for 2, we have a point for 3, we have a point for 4, and we have a point for 5. These are called the vertices of the graph. And then we
Okay.
make an arrow from X to Y if there is an ordered pair X comma Y.
Okay.
So we have ordered pair 3 comma 2. So we can draw an arrow from 3 to 2. You got to put your arrowheads on it.
Okay.
What else can we do?
We could draw one from four to two.
Okay, let's draw one from 4 to 2. Good. What else?
Four to three.
All right, 4 to 3. Anything else?
Five to four.
5 to 4,
Five to three.
5 to 3,
And five to two.
and 5 to 2. Good. I'll leave you with one to do later.
Okay. Wow, that's a lot more simple than
I
No, I'm
know it's
sleeping.
real simple.
It's not even like that
It's
complicated.
right. Okay. So here's a do later. We'll just call it
Okay.
example two. Let's let A be the same set, 2, 3, 4, 5. And
Okay.
we're going to define a binary relation, curly R, on A as follows. X comma Y is in curly R if and only if, running out of ink here, X and Y have a common prime factor. I think there was one like this in WebAssign.
Okay.
And this one is going to be kind of interesting because we didn't have any ordered pairs where the first and second coordinates were the same in the first example, right? Because X had to be greater than Y in for the first coordinate to be related to the second coordinate, right? But
Hmm.
here, X and Y having a common prime factor, in other words, X is related to Y, if and only if X and Y have a prime factor that they share. This is going to be a little interesting because when you look at these numbers, they're all big enough to have a prime factor,
Yeah.
and they all share a prime factor with themselves. So there'll
Yeah.
be some ordered pairs in here where like 2 is related to 2 because 2 shares the prime factor 2 with itself.
Yep. Yep.
So for part A, you can find R. And there's also some symmetry here.
Yeah.
2 shares a prime factor with 4. In fact, we can
Hmm.
make this a little bigger. We can add a 6 in here. Let's make this a little more interesting. Let's add 6 in here. 2 and 4 share a prime factor, right?
Yep. 6 and 3.
6 and 3. But you can put 3, 6 in there, but you can also put 6, 3 in there
Yeah.
because there's a symmetry with this requirement. Having a prime factor that they share means X, if X is related to Y, then Y will be related to X.
Yep.
So you'll have, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I think they're going to be 11 ordered pairs.
Oh,
So you can have fun with that one later.
yeah.
Okay, Alex, it's your turn. Do you have a question?
Um, Let me look back at
All
I
right.
have list of questions in my notebook. I gotta find it real quick. If anyone else has a question, they can ask first.
Well, Nura's here. Nura's always here. So Nura, how are you?
Good evening, Professor. How are you?
Well. We have a storm here at my place. Is it storming where you are?
It sure is. Some thunder and lightning.
Yeah, it's good old spring storm. Do you have a question that I can answer for you?
Yes, I do. It's about binary relations, and
Okay.
basically, it's just an extension of what you're doing right now. I'm a little just the definitions of the relation. So, a binary relation R from A to B. I'm looking at the Measure 2 material for 8.1, I think.
Uh-huh.
And that's the same as saying the relationship of A times B, like a subset of the relationship of A times B.
Are you looking for the definition of a binary relation from A to B?
Yes, I think that's what I am looking for. I'm getting the subset and I don't know, I'm getting a little confused with this.
All right, well, we have two definitions. The first one would be about a relation from A to B. So given sets A and B, any subset of A cross B is called a binary relation from A to B. Whereas if A and B are the same set, in other words, we just have one set, given a set A, any subset of A cross A is called a binary relation on A. Instead of saying from A to A, we say it's just a binary relation on A. But we could say from A to A. But we generally just shorten it up and say it's a binary relation on A. So, I mean, go ahead.
So when we're given some condition, for example, what you were just doing, where x was greater than y, that's some condition. We choose our subsets based on that condition.
That's right. So we can do another example where we have a different A and a different B. Let's let A be the set containing 1, 2, 3, 4, and 5, and B be the set containing 2, 4, 6, and 8. And we can define a binary relation. Let's call it J from A to B as follows. XY is in J if and only if Y minus X equals 2. Okay, in other words, X is J to Y if and only if Y minus X equals 2. And you could rewrite this equation. That means Y equals X plus 2, if you want to look at that a different way. Or, you could look at it as X equals Y minus 2, whatever helps you see that this relationship between X and Y has to satisfy this equation. And you can rewrite that equation in different ways to help you. But, we can find J. And we can't find the directed graph for this binary relation because directed graphs, we only play that game if it's the same set crossed with itself. We only play the directed graph game if it's a binary relation on a set. When it's two different sets, there isn't a directed graph game, okay? So let's find J.
Okay, so
So what should we? Yeah. So it might even be helpful, to look at, this relationship between X and Y, where you're looking at X, and figuring out, oh, X has to be 2 less than Y. Or maybe it helps you to realize once I'm looking at an X, I'm going to look for a Y that is X plus 2.
So we could choose we could let x be 2 and y be 4,
That would be in there.
and let x be 4 and y be 6.
Yep, that'll be in there.
Let's see, I think let x, no, I said 4 and 6, 2
I
and
think
4.
that's it.
Yeah.
Yeah, because I skipped and I only put the even numbers here. So only 2 and 4 are going to have a number in here that's 2 bigger than them because they're the only even ones. Okay. So I'll give you a do later.
Okay.
We can let A be the set containing 1, 2, 3, 4, 5, and we can define. Oh, I'll give you another B can be 1, 2, 3, 4, 5, 6. And we're going to define J the same way. As in example 3. You'll find J. And you'll have some more you'll have more ordered pairs than we did here. You could play the same game on A and say, hey, you know, I'm going to define a binary relation on A. In other words, you know, A gives the first and the second coordinate with the same rule. Or you could play the game on B, you know, if you wanted more practice. Did that help?
Yes.
And this rule, whatever it is, I mean, there are different ways to define rules.
I did the WebAssign and I was actually doing the measure to material and I was like, wow, I'm not really familiar with this. And then I thought, oh no, I bet we have a WebAssign. So, but in the WebAssign, there are a lot of values in each of the A and B sets. So there are a lot of ordered pairs that can be determined. Um, do you recommend that we just kind of write them all out or
Depends. You know, if you're not asked to do that, there might be a reason why you're not being asked to write all the ordered pairs. You may just see in WebAssign, are they asking you to write all the ordered pairs? Or are they
no?
asking you if certain values are related to other particular values or fill in the blank kind of stuff?
Yeah, like that.
Yeah, when it's yeah. I mean, it can be impossible to write all the ordered pairs if it's a binary relation on an infinite set. I mean, we can define, I gotta throw that pen away. A binary relation, curly R on Z as follows. AB is in the relation if and only if 2 divides A minus B. We could, this is the same thing as saying that A mod 2 equals B mod 2. You know, we could define it, you know, that way. These mean the same thing. Because if 2 divides the difference between A and B, it means either A and B are both even or A and B are both odd. And that's what it means for their mod 2 values to be the same. It means A mod 2 is either 0 or 1, right? And if it's equal to B mod 2, then they have the same remainder when they're divided by 2. That means either they're both even and their remainders are both 0, or they're both odd and the remainders are both odd. You know, the remainders are both 1. But that amounts to looking at the distance between A and B on the number line. And if that distance is divisible by 2, then A and B have to have the same parity. This only happens that 2 divides A minus B if A and B are both even or A and B are both odd. So these are just 2 different ways to define the same relation. But I wouldn't want you to try to sit there and write all of the values, the ordered pairs in this binary relation, because you can't, because it's infinite. There are infinite number of ordered pairs in this relation. But you could do things like, you know, find an A in Z such that, you know, A comma 3 is in R, or A comma -4 is in R, or find a B in Z such that -1 B is in R, or, you know, 6 B is in R. There'll be lots and lots of A's that could fill in this blank. Same here. Same here. Lots of B's could fill in either blank. you want any help with that? Do we want to find an A in Z such that A is related to 3?
Yes. So just looking at the 3, it would be 3 mod 2 would equal A mod 2.
That's right.
Hmm.
A mod 2 has to equal 3 mod 2. But what is 3 mod 2?
1, I would hazard.
It's a good hazard. So any A that gives a remainder of 1 when you divide it by 2 is going to be congruent to 3 mod 2. In other words, we'll pair up with 3 as an ordered pair in the relation. So
So
what,
we could,
yeah, possible A's.
well, we could say 5,
Yeah, A equals 5 would work fine.
but can we use 3 for A?
Sure, you could use A equals 3 because it has the same remainder as itself. You could put
Okay,
any odd number in there.
uh, right, yeah. 7, 9.
Yeah,
Okay.
and negative ones as well. And here, that's related to -4. What A's would be related to -4?
Let's see. That would be -4 mod 2 would be 0. It would give us a remainder of 0. So 4
Yeah,
mod 2.
yeah. Or even A equals 0 because 0 is even as well.
Yeah, that reminded me, as for questions where factors are considered, should we take 0 as a factor?
No,
Okay.
0 is only a factor of 0
Okay.
because from the minute you're multiplying other factors by 0, the resulting product is always 0.
Okay. There was something in WebAssign that had us look at that.
0 as a factor?
Yeah, I have it up. I can bring it out.
Yeah, let me also grab our WebAssign too, so that I can look at that and tell me which problem it was.
Yeah, it was problem 3, letter C.
In section 8.1.
Yes. No, no,
Holy,
no. It was problem 1, letter C. I'm sorry. In 8.1, yes.
holy cow, I just opened this up and I've got 14 communiques. 14 communications. Holy cow. I wonder if somebody's suddenly thinking they want to do the homework. Okay, I'm going to share my screen. Somebody. Just check that the other day. All right, here we go. Let's it doesn't matter which one I pick because they're both. All right, so 8.1,
Uh-huh.
problem number 3.
Problem number 1, letter C.
Okay. So M is P to N if and only if M and N have a common prime factor. Yeah, and remember, 0 is not prime. It's a common, not a common factor, it's a common prime factor. What's the smallest prime?
2.
So we're looking,
But is
have a,
it right to assume that 2 is a factor of 0?
oh, sure.
Okay. Okay. I misinterpreted that.
Oh, no, that's okay. It's not right, but you're worried about 0. 0 isn't the factor. 0 has a factor. In fact, any integer divides 0 because,
Okay.
right, we've seen that many times, like in our induction proofs. Here's just a fact. N divides 0 for any integer n not equal to 0. And we really don't want to say 0 divides 0, but n divides 0. Why? Because 0 is equal to n times an appropriate integer. What is the integer?
0.
Yeah. And that's just the weird thing that happens, when 0 is the product 0 is also the factor. And this is an integer. So yeah, 0 is going to be p to 2 or 3 or 5 or anything else, because 2 and 3 and 5 all divide 0, and 2 and 3 and 5 divide 2 and 3 and 5 respectively. Did that help?
Yep. Yeah.
Yeah, that's a little
Thank
fine-tuned point. Yeah, that's a good question. Thank you. Other questions?
Could we go over strings?
Yes. The strings are really fun. There was a nice little problem in the WebAssign about, this is number 4 in section 8.1 WebAssign. And it says A is the set of all strings of 0s, 1s, and 2s. A is called the alphabet. In other words, we're building strings using this alphabet. And that's why we call it A for alphabet. But here we're restricting ourselves to just look at strings of length 4. All right, so before we even go any further, let's just write down some of the strings, and then we can write down the whole definition of the binary relation, where I think we add up the sum of the digits. Is that what it is?
Yeah.
And if the sum of the characters in S equals the sum of the characters in T, we say that S and T are related. And you can play this game even over a smaller alphabet of just the binary bit alphabet with 0 and 1. But first, let's find some strings. They're calling A the set of all strings. Oh, fine. I hate that, because it should be S is the set of all strings, and then the alphabet is A, but they called A the set of all strings. Okay, so it's over this set. Let's find some strings in A.
Okay.
All right. So it's
Let,
all strings of length 4, and we can use 0s, 1s, and 2s. So,
let's do 0, 0, 1, 2.
yep, there's one.
1, 0, 2, 0.
Good. So you have,
1, 0. Oh, I'm
go ahead.
sorry.
Go ahead.
0, 0, 2.
In fact, we can count how many strings there are in this set. We can count how many there are. Let's just see how many choices we have. We have to pick the first digit. And then we're going to pick the second digit, and it's the multiplication principle in play as we count how many strings we can build using this alphabet with 0, 1, and 2. How many choices do we have when we're picking each digit?
3.
That's right. So we have 3 choices for the first digit, and we can mix and match that with all 3 choices for the second digit. 3 choices still, 0, 1, or 2 for the third digit. So this is 3 to the 4th. Strings in A. So there's a bunch of them in A. We don't want to find them all. But I mean, if you wanted a methodology, for finding them all, you could build, like, it'd be crazy, but you could build a tree where here's the first step is you pick either the digit 1, 0, 1, or 2, and then you pick the second digit, and it's 0, 1, or 2, 0, 1, or 2, 0, 1, or 2. See what I mean? Then you pick the third digit, 0, 1, or 2, 0, 1, or 2, 0, 1, or 2. And then you have to pick a fourth digit, and then, you know, things get kind of hard to draw, right? But, you know, at the end of the day, if you do this process, you know, you start from the root and you go to a node or a leaf out here. You just read off the string, like, you know, 0, 0, 0, 0. That's one of the strings in there. Or 0, 0, 0, and then go to the 1.
This looks like my programming class.
Right, right. So, you know, maybe here we'll go to the 2 here, and then you know, go to one of these, like 0, 1, 2, 0. But it helps, you know, it helps give a visual, you know, 0, 1, 2, 1, 0, 1, 2, 2. You know, you can do it, right? All right. So anyway, in this particular example, S is related to T. What did they name this relation? What was the letter they used? R. Okay. S is R to T if and only if sum of characters in S equals the sum of the digits, or they call them characters. I don't know. I would call them digits if I wrote this, because, you know, we're taking a sum. It makes more sense to call them digits. But were you able to answer the questions? You know, is 1, 2, 2, 1 related to 2, 0, 2, 2, and that sort of thing?
Yeah,
Yeah.
yeah.
I mean, it's an interesting relation because it actually groups. What is 3 to the 4th anyway? It's 29, it's 81. There are 81 strings. And you could actually split into, you could partition A, as a matter of fact, into subsets where each subset is the elements, the strings that are related to one another. Like 0, 0, 0, 0 is in a subset all by itself because there is no other string whose sum of digits is 0, but 0. So it's by itself. But there are 4 strings whose sum of digits is 1. And they could all go together in a little subset because they're all related to each other. You know, the sum of each of these is 1. So they all go together. And then you could look, you know, to try to build the subset, the partitioning set that has all of the strings whose sum of their digits is 2. You know, it would include strings like 0, 0, 1, 1, but would also include strings like 0, 0, 0, 2. And you can see there's going to be a lot of strings in here because 4 choose 2 is 6. So there are going to be 6 different strings that have 2 1s in them. Because there's 6 different ways to arrange, you know, 2 1s. 1, 2, 3, 4, 5. I'm missing one. Which one am I missing?
2000.
Oh yeah. I'm certainly missing a couple of the ones with the 2s. But I'm missing one of the ones that has 2 1s. Just trying to figure out which one it is.
Do you have 0110?
Oh, good. That's it. That's the one I'm missing. So these are all related to each other, and they would be in a partitioning subset together because they all have the same sum. And then you could just keep finding, you know, then you would look at all the strings whose sum of digits is 3. They would all be related in one of these subsets, all the way up to the maximum, which would be a loner string, just like this was the loner string. The string 2, 2, 2, 2 is the only string whose sum of its digits is 8. So it's not related to anything but itself. And this is an interesting example of something we didn't have time to study called an equivalence relation, where you have a relation where inside a subset, every element is related to every other element that sits in that subset, and it winds up partitioning the underlying set. In this case, the set of all strings of length 4. over the alphabet having 0, 1, and 2 as its characters. And I'm sorry we didn't have time to do that. But you can read that. If you read section 8.2 and 8.3 in your textbook, you can learn about equivalence relations. They're very interesting. I would download the book while you still can. I would just download the whole ebook and save it as a
That is
reference.
a really good idea. I will do that.
I would do it. Yeah, put it on a little, thumb drive, and label it. Yep. Other questions?
Give me 1 second, refresh. I have one.
All right, I'm going to pause the recording while you look for your question.
Yeah.
So Noah was asking about sequences. Here's our definition of an arithmetic sequence. And it's got this special form where you have an initial term, A naught, but then the next term you get by taking A naught and adding D. Well, the next term you get by taking A naught and adding 2D, which is the same thing as taking A1 and adding D. And you get A3 from A2 by adding another copy of D, which is a grand total of adding 3 copies of D from A naught. So you can either think about the common difference, the difference of consecutive terms like A3 minus A2 or A2 minus A1 or A1 minus A naught. That's what we mean by A sub k plus 1 minus A sub k. Or you can think of it in terms of a general formula. And this is the general formula for an arithmetic sequence. And here's an example that I think we've even seen in class. It's just one for some reason that pops in my head because I like starting with 5 and I like adding 3. But the same idea is with geometric, but except for a geometric sequence, it's a little different. A geometrics, and again, if I bug out, it's because of energy. BGE is trying to have a storm here. It's a sequence of the form, and the way we get it is A naught, and then the next term would be A naught times the common ratio R. We're multiplying by R over and over and over again, right? And it's got an initial term, A naught, and common ratio, R. So there's our general formula.
So the general formula is like, oh, go ahead. No,
You tell
actually,
me.
okay. So the general formula is an goodness, I can't say it. Arithmetic and not geometric. So it would have to be something that's like factorial.
Well, what are we
Well,
doing here?
oh, that is,
We
mm,
are multiplying, but we're
yeah.
just multiplying by R over and over again to a grand total of n times.
Uh,
Like, think about it. When n is 0,
yeah.
exponent is 0, and R to the 0 is 1. So A naught just equals A naught times 1. When we're trying to
Okay.
get the next term, A1, n is 1, well, it's A naught multiplied times R once, R to the 1. If we want to get term A sub 2, this is A sub 2, we take A naught and we multiply by R twice. In other words, by R squared, because multiplying by R times R again is multiplying by R squared.
Okay.
And that common ratio, well, the common difference was a term minus the term before, but that was because we were adding D. The common ratio, the common ration, the common ratio R, it's A sub k plus 1 divided by the term before. Like you can check it. Like here we checked in this example, we checked that A3 minus A2. Oh yeah, A3 was 14, A2 was 11. That difference is 3. A2 minus A1. Oh yeah, 11 minus 8 is 3. A1 minus A0 gets back to the beginning. Oh yeah, that difference is 3. But in a geometric sequence, we can see things happening because of dividing. Like, consider this sequence. We're doing something to get from term to term. Aren't we multiplying times 2?
Yeah,
So the common ratio is 2. So the general term looks like a sub n is the initial term, which was 3, times 2 raised to however many times you need to raise it, which is n.
got it. And okay,
And
I think
then
I
let's look
understand.
at, let's look at a sub k plus 1 divided by a sub k, okay? So let's look
Okay,
at, this is a sub 1, this is a sub 2, because this is a sub naught, right? This is a sub 3, this is a sub 4. So if we look at a sub 4 divided by a sub 3, okay, so 48 divided by 24, oh, that's 2. We'll look at a sub 3 divided by a sub 2. Oh, that's 24 divided by 12. See what I mean?
yeah,
That's why it's called a common ratio, because it's the ratio of a term divided by the term prior. It'll always wind up being the same value. But
got
it's,
it. And it's not geometric because we're using the same term to multiply it over and over again. It's not like
it is
multiplying.
geometric. It is
Oh,
geometric.
it is geometric. So I was thinking it was general.
It's not arithmetic.
That's not
We're
arithmetic.
not
Okay,
adding something over and over. We're
okay,
multiplying by something over and over.
got
And
it.
that's
Got
the very definition of a
it.
geometric sequence. Is when we
Okay,
do iterated multiplication as opposed to arithmetic when we're adding the same thing over and over. Iterated addition, that is an arithmetic sequence, but here iterated multiplication, that is a
um,
geometric sequence. That's just the definition. That's just
okay.
the
Oh yeah,
word.
I was getting confused with the general and the geometric because the general is for the
General
power
formula as opposed to
races. Yeah,
geometric, right?
yeah. So I was raising the
Right.
power.
This is the
Like okay,
general formula for this particular geometric sequence.
yeah.
Whereas, this has general formula. Well, you tell me,
Of a
what is a sub n going to be? It's a naught.
plus 3
N.
and got it.
Yeah,
Okay,
we're using, 3n.
got it. Okay, so the general formula is whatever formula you find through your arithmetic or geometric sequence, in
That's
a
right.
sense. So
And the
got it.
sequence
Okay.
might be neither. You can have a sequence that is neither.
Oh
Okay, and I'm going to refer you to the measure two material on that.
yeah.
And the
Okay.
solutions are posted, and they took
Okay.
hours to type up. So maybe you'll
Okay.
actually crack that open and read that.
Yeah, I'm gonna read that.
Hi, David. I
Thank
see that you came into the room. How are you?
Hey, so, um, I think I needed help for something on test three, or I needed you to clarify something really quick.
Sure,
Could you clarify like mutually disjoint really fast?
absolutely. Okay, so mutually disjoint sets. It's just an extension of the idea of disjoint sets. Okay, so here's our definition. A collection of sets, just call them A1, A2, dot, 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 A sub K, is a mutually disjoint collection if A sub I intersect A sub J is empty whenever I is not equal to J. All right, let's look at an example and let's look at a non-example, okay? Is this a mutually disjoint collection? I'm going to say A1 is going to have the element little x, little y in it. A2 is going to have the elements little w, little z, little t in it. And A3 is going to have little t and little z in it. Get a mutually disjoint collection. In other words, we check A1 intersect A2, and we check A1 intersect A3, and we check A2 intersect A3. We need to get the empty set because I and J, here I is 1, J is 2. Here I is 1, J is 3. Here I is 2, J is 3. Okay? Like we don't require that the intersection be empty if these two indexing numbers are the same. Like we don't expect A1 intersect A1 to be empty. That would mean all these sets have to be empty sets, and we don't want that. It's just that if you're looking at the intersection of any two of these two or these two or these two, you want that intersection to be empty. Well, when we intersect A1 with A2, they don't have any elements in common, so that's empty. What about A1 with A3? Do they have any elements in common?
No.
All right. What about
Okay.
A2 and A3?
Yeah, they do.
And that's not empty. So the answer is no, because
Okay.
that. So any two, you have to look at them pairwise. Okay.
Okay. Thank you.
You're so welcome. All right, now Alex, I see that you've asked for like 7 extensions, and you've asked for extensions on a bunch of really old homeworks. I'm gonna extend 7 and 6. Okay,
Okay, thank you so much, Professor.
you're welcome. But I mean, I would start with whatever is most important for you, as far as whatever you don't understand. Start with those first. But I definitely think that 7 should help you, prepare for the exam. Okay.
Okay. And I had a question about the exam. It's gonna be 15 questions, right?
Well, I didn't tell you exactly how many there were going to be, but it's got to be reasonable because you have 75 minutes for a regular exam, right? And a regular exam, um, it has what, 10 questions usually?
Yeah, like 10, yeah, I think so. Okay. About 10, yeah. 8 to 10.
Yeah, so I mean, it's got to be, reasonable.
Yeah.
Professor, if we need a calculator, would they have one at on Saturday in like one of the
No,
rooms, or
what, you don't have a calculator?
no? I don't. I lost my calculator during last semester when I was taking
Shucks.
calculus.
Um,
Yeah.
yeah, I'll probably have a couple of spares with me.
Okay.
So get
Thank you.
there early so that you can snag a spare.
Okay, definitely. And it's 3 to 5 tomorrow, correct?
It
In the
is,
science building.
it's 3 to
Okay,
5 in the science building.
got it.
And it's in fact, maybe I'll put it on the first page of these notes. The final exam, it's in SC 2321, I think. Somebody check the reading page. I've got it posted all over the place. Please, somebody check the reading page and make sure I'm remembering that.
You're right. Yeah,
Okay.
S3 2321.
Okay,
That's right.
that's the main floor.
Okay.
So I'll see y'all there tomorrow.
Awesome.
And
Is
then
it all the discrete math classes or just our classes going to be in that?
just my classes. Other
Okay.
classes are sitting, different professors do different things. People that
Okay.
are only teaching one section probably didn't select the Saturday common final time. But those of
Uh,
us who are teaching 2 or 3 sections, like next
yeah.
semester, I'm going to teach 4 sections. It's nice to knock out the final exam
Yeah.
all at one time. So, I don't have to sit there bored to tears for 2 more
Yeah.
hours. All right, so get there early. I'll be sure and grab a calculator. I'm not even sure you actually need a calculator tomorrow.
Yeah. It doesn't really look like we need one, but I'm just thinking of like the problem that we had in like test three that might pop up.
Right.
Yeah.
Really quickly, Professor, I went to the review that was given by the homework lab or the math tutoring lab or whatever,
Yeah, how
and
did that go? Were you in person or were you in Zoom?
I was in person.
And how did that
Um,
go?
It was really interesting. I thought it was good. It was really great exposure. They had a lot of proofs. Nothing that they did was completely unfamiliar to me, but the level of the questions I felt like were a little beyond what we did in class. I took notes though, and he asked a question about relations, but he asked us to prove whether or not the relation was reflective, symmetric, or transitive.
Yeah, yeah, we didn't
And
get to
I'm
that.
Yeah, I'm wondering if we're going to see anything like that on the test tomorrow.
No, you know me better than that. I
Okay.
would never, no, because we did not get to section 8.2, which is the section where you learn reflexivity, symmetry, and transitivity. I tried to mention
Okay.
it a little bit, that when
You
there's,
did mention it in class that
where
we
the
didn't.
arrow goes both ways, we have symmetry, and if there's a loop at every vertex, you have reflexivity because the element is related to itself. And transitivity, is a closure where if 2 is related to 3 and 3 is related to 4, then 2 has to be related to 4. And I feel bad that we didn't get to that. So, but you felt like the proofs were at a different level on other material or just on the
No,
material?
no, I felt like I was able to keep up with everything. I had no problem following along. I just felt like some of the math that the presenter used was like we didn't get quite up there. Like he had one problem, and I took a lot of notes, and I got my notes in front of me. It was a function, and it was the set of all real numbers minus zero mapping to the set of real numbers. And then he had f of x equals x plus 1 over x squared. And then he had for any x sub 1, x sub 2 in the set of r minus 0, simplify f of x sub 1 equals f of x sub 2. So,
Well, it's because it's a proof of whether or not that's a one-to-one function. And you're right. I went light on the algebra on the one-to-one functions. And that is a classic example, the one you're mentioning, because I felt like people hardly even followed my simple linear explanation. And I'm very sorry that I didn't feel like I could push the algebra. And some professors choose to push the algebra, and I choose to push the logic because I feel
well,
like students have a better shot at the logic than at a really gnarly algebra problem.
yeah, yeah, the presenter actually had a hard time with this one. But I really appreciate that style of teaching that you did for us. I was able to follow along with everything. Yeah, I thought it was helpful.
Well, thank you so much for sharing that. Yeah. Um, there's a lot more to this course than we covered. And things you just have to kind of I don't teach down necessarily, but I do try to teach to my audience. I try to evaluate the audience fairly early on in the semester, and I can base that on everything from attendance to how people are doing on WebAssign to the kinds of questions people are asking, because I can see all that. I can see how people are doing on WebAssign. And I can see, what kinds of responses I'm getting on quizzes, and I do teach accordingly. So anytime you want to pop in and ask a question, if you download your book, I'll be glad to answer it for you if I can.
Oh, that's great. I really appreciate that.
Yeah, you'll challenge me. I'm sure you'll come up with a question. I'll have to read the book and learn it myself because there's a lot in this book, there's a lot that, we don't teach. And Epp knows her stuff. She really does. The author, man, she is good. We're really lucky to have this book. All right, I'm going to say good night and pleasant evening, people. But be sure and get some sleep. That's the most important thing. Don't stay up all night doing WebAssign. It won't pay off the way you hope. Get some
Thank
sleep.
you, Professor.
You're welcome.
Yeah.
Thank you for a
Thank you,
lovely.
Professor.
Good
You're
night.
Thank you.
welcome.